After we apply the Newton's equations and generalize them for the system of particles, we can work on the work energy equations. As we have derived the equations for the particles, we're going to make use of that for each particle of the system of particles. Therefore, we need to have a subscript denoting the particle I here, and this left-hand side is the total work done by all the forces, non-conservative and conservative forces, all of them, results in the change in the kinetic energy of the ith particle, and the kinetic energy of the ith particle is defined in this way, which is the same type of descriptions that we did for the particle, so it's nothing new. The only thing new here is that now we have a subscript for each for defining each particle. Therefore, this U1 to 2I is the work done on Mi particle or the I particle by external and internal forces, conservative and non-conservative forces acting on particle I from the first situation to the second situation. And we can find the sum for all particles, and this U1 to 2 defines the summation, so we define it as a summation here, the summation of the work done on each particle results in the total work done on the system of particles by all forces, internal, external, conservative, non-conservative, all forces, which results in the change of the kinetic energy of all particles, summation of the kinetic energy, change in the kinetic energy of all particles defined as delta T here. And this is the total kinetic energy of the system of particles. Now, we can do some assumptions and then simplify this concept. For the particles which are rigidly connected or particles that are connected by frictionless joints, when the particles are actually rigidly connected to each other, then it becomes a single rigid body. So that's the rigid body concept. If we have the rigid body concept, that means, or the particles are connected by frictionless joints, it's kind of a robotic system. So you have this first revolute joint, then you have a second revolute joint, similar to the robot actually that you saw in your midterm exam. If these joints are frictionless, then the work done by the internal forces cancel out, because the work done here by the internal forces are the reaction forces, and they do not result in any type of motion, and they are back and forth in opposite directions for this particle and that the other particle, so they cancel out each other. In this case, what we say is the equation actually stays the same, but the definition changes a little bit. In the definition now, this total work done is by all external forces and work done by spring forces and gravitational forces, if there is any, and gravitational forces. So we need to also say these gravitational. Let me just shortly write gravity. Okay, so in that case, we have this change in the work energy concept. Again, this is for the rigid bodies, or in other words, for the particles that are rigidly connected to each other, the same definition actually, or the particles that are connected by these frictionless joints. In that case, we can exclude the work done by the internal forces. Now, also we can separate the work done in this way. This is something we did for the particles as well, so this is the same idea, nothing different. This time this is the total work done by all the non-conservative forces is equal to the change in the total kinetic energy plus the change in the total potential energy due to gravitation and due to elasticity. in the system of particles. And as a last step to generalize this concept, now we can work on the kinetic energy information. For each particle, we're going to write the kinetic energy equation in this way. So the kinetic energy for the ith particle, so this is Ti actually, Ti is equal, well, this is not Ti, sorry. This is the total kinetic energy because we were doing this summation. Inside the summation is the kinetic energy for a single particle that we already know. Now Vi is the velocity of the ith particle and it's defined as an absolute velocity. So it should be measured with respect to a inertial frame, and this is our inertial frame right over here. And how it is calculated is by deriving the Ri vector defined from the inertial frame to this ith particle. And Ri, in fact, can be defined by this vector defining the location of the mass center plus the relative location of this ith particle with respect to the mass center. Now that is defined by rho I vector. So if we do the derivation with respect to time, then we get this Vi that is equal to velocity of the mass center and the change in the position of the ith particle with respect to the mass center. Now this change, if you're thinking about the rigid body concept, then you might say, well, this shouldn't change, but actually if the rigid body is rotating, then it will change the location of this vector, not its magnitude, but its direction will change, right? So there will be a change, and this will appear for any mass system. This derivation will appear for any mass system. And this is defined as the relative velocity of the ith particle with respect to the mass center. Now, if we work out this equation and then substitute for Vi this information now, which is defined with respect to the velocity of the absolute velocity of the mass center plus the relative velocity of the ith particle with respect to the mass center, and rewrite this equation, then we get this longer part of the equation. Now, in this longer part of the equation, here we have this term which includes the velocity of the mass center. Well, this is a constant, it doesn't have a I subscript, so we can move it out of the summation. If you move it out of the summation, then we are left with mi times rho I dot, which means you're taking the derivative of mi rho I vector with respect to time times the velocity of the mass center. Now, this is defined as the first moment about the mass center, and it is equal to 0. Let me just show you a simple example. If we have these two particles and their mass centers is in the middle, so that means that these two particles have the same type of, so this is the mass center, and they have the same type of mass. Now the vector defined from this mass to the, or from the mass center to this, let me just try to redo that, from the mass center to that particle is, let's say, R1, and the other one is R1 again, and this is, let's say, this is the left, to the left is the positive direction, this is the negative direction. Then M1, well, M's are equal to each other, let's call that M and M. Then about the mass center, the moment calculated for them will be negative M times R1 and plus M times R1, and they're going to cancel out each other. And this is the general idea of the first moment of mass about the mass centers. This is a concept that you should already seen in your statics course. And this is equal to 0. This is equal to 0. So that part cancels out, and we are left with the velocity of the, well, this part totally cancels out. This part totally cancels out. So we are left with the kinetic energy defined with respect to the mass center for each particle, and then kinetic energy defined with respect to the relative motion of this mass I with respect to the mass center. So we get a general formula. In this general formula, this part is defined as the kinetic energy found by using the absolute velocity of the mass center, and the part on the right, this is the kinetic energy due to the motion of particles about the mass center. And this is valid for any mass system. This is valid for the rigid body systems as well. And you might disagree with me and say that, well, we know from our previous lectures that we have m times v squared for the particles. Yes, this is for the particles, but when you talk about the kinetic energy for rigid body systems, then you need to also account for the extra term due to the rotation of the rigid body. Okay, and then in general you have, if this is a planar motion concept, then you would have this I as the moment of inertia about uh, the normal of that plane. Omega is the angular speed of the particle, so you have this extra term, which is actually derived directly from this term. Okay, this is a more general concept. This is a little bit constrained, and the constraint here is that you're only taking into account the rotation of the rigid body. Otherwise, if the rigid body is not rotating, then the particles that compose this rigid body are not moving relative to each other. Okay? The most general equation for the kinetic energy for any mass system is written in this way.